Grade 12s, today we will investigate standard electrode potentials and discuss the conditions under which they are determined. And then we will describe the standard hydrogen electrode and its role as the reference electrode. Let's join Simbulelo to help us with these concepts. We start off with what an electrode potential is.
Let's begin by taking a closer look at a zinc half cell that's not connected to any cell. In the electrolyte solution of zinc ions, the number of positive ions is equal to the number of negative ions. The solution is electrically neutral. The zinc plate is also electrically neutral because it's made up of zinc atoms that have the same number of protons and electrons. But when we place the zinc plate into a solution of zinc ions, a reaction occurs that changes this electrically neutral situation. A zinc atom from the electrode loses 2 electrons to form a zinc ion. We can represent this reaction by writing the oxidation half reaction. Zn goes to Zn2 plus 2 electrons. The electrode is now negative because it has 2 extra electrons. And the solution is now positive because it has gained zinc 2 plus ions. We give this difference in charge a special name too. We call the difference in the charge between the electrode and the electrolyte solution the electrode potential. Now, there's an imbalance in the charge in the half cell, and this imbalance needs to be reversed. The interesting thing about oxidation and reduction half reactions is that reduction is the reverse reaction of oxidation. So a reduction reaction can reverse the electrical imbalance. The extra electrons on the electrode attract a zinc ion in the solution. The zinc ion gains 2 electrons and forms a zinc atom on the electrode. This is a reduction half reaction and is written as Zn2 plus 2 electrons goes to form Zn. In the unconnected half cell, the rate of oxidation is equal to the rate of reduction. This means that a chemical equilibrium is established. Let's take a look at the 2 half reactions again. To represent a chemical equilibrium in a half cell, chemists always write the reduction reaction as the forward reaction and the oxidation half reaction as the reverse reaction. And when we rewrite the oxidation half reaction, we write it from right to left and then combine them into a single equation.
Oh, now I can see. Reduction is the forward reaction. Oxidation is the reverse reaction. And the 2 reactions take place at equal rate in the zinc half cell, I suppose.
Yes. And that means a chemical equilibrium is established and there's no change in the concentration of the zinc ions in the solution. The half cell is electrically neutral, although there are continuous changes happening at a microscopic level. We observe no measurable potential difference between the electrode and the electrolyte on a macroscopic level. So we must conclude that the electrode potential for this half cell is 0 volts.
The electrode potential of a single half cell cannot be measured. The electrode potential can only be measured relative to another electrode. For this reason, a standard electrode is chosen against which other half-cell electrode potentials can be measured. Simbulelo will tell us now how we can find the electrode potentials of different half cells with the use of the standard hydrogen half-cell electrode.
If we want to arrange half cells according to those with electrodes that are the strongest reducing agents to those with electrodes that are the weakest reducing agents, we need 2 things. Firstly, we need a half cell against which we can compare all other half cells. We call this the standard half cell. And the hydrogen half cell has been chosen as the standard half cell. Secondly, we need a set of conditions that will make the comparison between the different half cells and the standard hydrogen half cell fair. These conditions are called standard conditions.
That seems to be important in all science experiments. It would be impossible to compare two things if other conditions did not stay the same.
Exactly. Every experiment must be a fair test. The standard conditions for a half cell are as follows. The temperature of the electrolytes must be 298 Kelvin. The concentration of the electrolytes must be 1 mole per decimeter cubed. And for electrodes that use gases, the gas pressure must be 101.3 kilopascals. Let's take a closer look at the standard hydrogen half cell. This half cell has a special glass electrode that contains a platinum plate. Hydrogen gas is bubbled over a platinum plate into an electrolyte containing hydrogen ions. The equation that represents the chemical equilibrium established in a hydrogen half cell is written as 2H plus aqueous plus 2 electrons is in equilibrium with H2 gas. Platinum plays no part in the reaction, as it's an inert metal that simply provides a surface for the gaseous hydrogen to react with hydrogen ions in the solution.
Does that mean hydrogen is a strong reducing agent?
Not really, Nombulelo. Hydrogen is not a very strong reducing agent, but it's also not a very weak reducing agent. This is one of the reasons why the hydrogen half cell was chosen as the standard electrode. Hydrogen occurs in the middle of the range of reducing agents. That means its electrode potential is in the middle of the range of values for reducing agents. We call this electrode potential the E0 value, and it is measured in volts. Remember, we can't measure the electrode potential between the electrode and the electrolyte of the hydrogen half cell directly. Instead, chemists gave the hydrogen half cell an E0 value of 0.00 volts. Although some electrodes of half cells will be stronger reducing agents than the hydrogen electrode, some will be weaker reducing agents. So when we connect a half cell to the standard hydrogen electrode, we use a center zero galvanometer in the external circuit. The needle can move to the left, giving a negative reading, or it can move to the right, giving a positive reading. When we combine a zinc half cell under standard conditions with the hydrogen half cell, we form a galvanic cell. And the reading on the galvanometer is negative 0.76 volts. So what can you deduce about this negative value? The negative reading on the galvanometer indicates that the zinc half cell is more negative than the hydrogen electrode. So the zinc electrode must be the anode in this galvanic cell. That means the zinc electrode is a stronger reducing agent than the hydrogen electrode. We say that the negative reading on the galvanometer is the E0 reading of the standard zinc half cell. So the zinc half cell has a standard electrode potential or E0 value of negative 0.76 volts.
Thanks again, Sumbulelo. We can write the cell notation for this cell like this. Since the zinc half cell is the anode, we start the notation with solid zinc that undergoes a reaction to zinc 2 plus aqueous with a concentration of 1 mole per cubic decimeter. This is followed by the double line of the salt bridge. The standard hydrogen electrode is the cathode. In this half reaction, the hydrogen 1 plus aqueous ions are reduced to form hydrogen gas. Since the inert platinum electrode was used in the hydrogen cell, it is included into the cell notation. It is always written to the outside of the cell as platinum with the symbol PT and S for solid in brackets. When the standard electrode potential of a substance is positive, the hydrogen is oxidized. The hydrogen electrode becomes the anode. The other substance becomes the cathode where reduction occurs. An example of that is the copper half cell. The reading on the voltmeter will be positive 0.34 volt. And the cell notation for this will first have the information of the hydrogen half cell, since it is the oxidation half reaction, and then the information for the copper half cell. On the table of standard reduction potentials, the different substances are arranged according to their cell potentials or E0 values. These potentials can be used to determine if a cell reaction is spontaneous or not. You can find some more problems in the task video. Practice these. Until next time when we look at these calculations. You'll also find more information on our website at www.mindsearch.co.za/learn. Goodbye.
From the electrode loses 2 electrons to form a zinc ion. We can represent this reaction by writing the oxidation half reaction. Zn goes to Zn2 plus 2 electrons. The electrode is now negative to any cell. In the electrolyte solution of zinc ions, the number of positive ions is equal to the number of negative ions. The solution is electrically neutral. The zinc plate is also electrically neutral because it's made up of
Grade 12s. Today we will investigate standard electrode potentials and discuss the conditions under which they are determined. And then we will describe the standard hydrogen electrode and its role as the reference electrode. Let's join Simbulelo to help us with these concepts. We start off with what an electrode potential is.
Let's begin by taking a closer look at a zinc half cell that's not connected. Zinc atoms that have the same number of protons and electrons. But when we place the zinc plate into a solution of zinc ions, a reaction occurs that changes this electrically neutral situation. A zinc atom